In this video, we will look at the properties of fine-grained soils such as clays and silts. Fine-grained soils, or fine soils, are also known as cohesive soils or non-granular soils. As mentioned, fine-grained soils are usually silts and clays. Silt and clay particles are very small and usually measured in micrometers. 1 micrometer is 1/1,000,000th of a meter. Put another way, 1,000,000 micrometers makes up 1 meter. Silt particles range in size from 60 micrometers down to 2 micrometers, while clay particles are smaller than 2 micrometers. Silt particles can only be seen in a microscope, while you would need an electron microscope to see a clay particle. The structure of silt and clay particles also differs. Clays are sheets of different types of compounds, such as silicon and aluminium compounds, whereas silts are granular, like very small sand particles. The sheet structure of clays has a large influence on its behavior. The small size of these particles means that the soil particles attract each other, and so the soil sticks together. This property is called cohesion and is one of the main differences between fine and coarse soils. You can see cohesion when you squeeze a sample of wet clay. It will stick together, while a dry sample will crumble when the pressure is released, as it has no cohesion. Clays have very strong cohesion when wet, while silts are less cohesive and can often be crumbled, especially as they get drier. Plasticity is the property which allows material to be deformed without cracking or crumbling. Wet clay has very high plasticity, while silt is not so plastic. A sample of wet clay can be rolled into a thin thread without breaking, while a silt will crumble. Another indication is that clays are also quite sticky when they're wet, while silt is not. Silts have low permeability and so do not drain very well. However, clays are even less permeable. Some types of clays are even impermeable when compacted. Impermeable means the water cannot move through the soil. So these type of clays can be used to line ponds and rubbish tips because the water is just not going to get through. One feature of clay particles is that they usually exert more influence on the soil properties than the actual proportions. This is why a soil which is mostly sand or gravel but has a small percentage of clay may well behave like a fine soil and be defined as such. The bearing capacity of clays and silts in the ground is usually in the range of 75 to 150 kilopascals, although very hard dry clays can get up to 600 kilopascals. However, clays and silts generally have lower bearing capacity than compacted coarse soils. The properties of fine soils change significantly according to the water content in the soil. For example, plasticity and cohesion increase as the water content increases to a certain point, then drop away. Bearing capacity also increases as the water content decreases, once again to a certain limit, then it drops away, as we'll explain in later slides. The water content of silts and clays is the main factor determining their properties, as they have different states according to the water content. At low water content, they are in a solid state where they are hard and brittle. You see this with a clay plate, which will break into pieces if you drop it on the floor. If more water is added, then the clay can be molded, but still cracks when you reshape it. Adding even more water takes it to the plastic state, where you mold the clay without it cracking. It can be manipulated like plasticine or blue tack. If you add even more water, then it enters the liquid state, where it flows and has no strength, like very wet mud. The boundaries between these states are called consistency limits. They may also be called attribute limits. These limits are the water content of a particular soil when it transforms from one state to another. For example, the plastic limit is the water content where a soil transitions from being semi-solid to being plastic. That is, when the soil has a water content below the plastic limit, it is in a semi-solid state and acts like a semi-solid. and when the water is above the plastic limit, it is in a plastic state. However, most soils, this transition happens slowly over a range of water contents, so the values of each limit are determined from a standard test, but do not mark a rapid change from one state to another. Clay does not immediately change from plastic to mud in seconds during a rainfall. It happens over a period of time as the clay gets wetter and wetter. One useful measure is the plasticity index, which is the water content at the plastic limit minus the water content at the liquid limit. This measure gives you a good indication of whether the soil is a clay or a silt, as well as how well it will compact and how strong it will compact too. A higher plasticity index indicates that there is quite a bit of clay in the soil. This means the soil is likely to be softer and weaker than other soils. It is also more prone to loss of strength as it gets wetter. Sediment is caused by voids in the soil being squeezed smaller. This results in the soil volume decreasing and the density increasing. The soil surface above the settling soil is lowered in response to the reducing volume. This increases the strength as it results in more contact between soil particles. We do not want a road to settle significantly after it is laid. This changes the shape of the road surface away from the designed shape. Also, if some areas settle more than others, then the road surface develops humps and hollows. This is called differential settlement, and it can occur when some areas are not as well compacted as others, or where there are different soil types, where soil conditions vary, or where a fill depth varies. So, when we are constructing earthworks, we want to make sure that the underlying soil and any fill areas have settled into a dense state before we grade the final formation level and start building the road pavement. There are several ways that settlement can occur. The first is the reduction in the void volume by air being expelled from the soil. We apply a heavy load to the soil, which forces the soil particles to move into the void spaces, as shown in the diagram to the left. This compresses the air in the voids and forces the air out of the soil mass. This process is called compaction. However, water is incompressible. When a load is applied, the void water will be under pressure, but it will not reduce in volume, so a void filled with water will prevent the soil particles from moving into the voids. The rate at which the settlement can happen depends on the permeability of the soil. The soil particles cannot move into the voids until the water has flowed out of them, and the rate of the water flows out of the soil mass depends on the permeability. The process of settlement due to the expelling of water from the voids is called consolidation. Consolidation is not usually an issue with coarse soils. They are usually highly permeable soils, so the water in the voids is able to flow out of the soil mass during the compaction process. However, fine soils have low permeabilities, and the water can take a long time to flow out of the soil mass. In time, excess pressure will force the water to flow out of the voids, and the soil particles will be able to move into the voids to form a dense mass. However, this can take months or even years for the water to flow out of the soil mass that supports the road. The load needs to be sustained, so semi-permanent loads such as piles of soil are placed and left for months. This is called preloading, and we will look at this in the construction project topic. It should also be noted that consolidation is usually only a problem for in situ fine soils where we cannot change the water content very quickly. It is not much of a problem for fine soils used to construct fills. This is because part of the fill construction process involves wetting or drying the soil to get a water content that will enable the soil to be compacted, but does not have the excess water in the voids that will prevent the soil particle moving into their most compact state during compaction. This water content is called the optimum water content. The optimum water content is the water content at which the soil can be compacted to its maximum dry density. It may also be referred to as the optimum moisture content. The maximum dry density is the maximum density that can be practically achieved with a particular soil. You'll recall that a soil is stronger at higher densities because there are more contact points between the soil particles. Therefore, the maximum strength of a soil is achieved when it's at its maximum dry density, and this can only be achieved when the soil is at the optimum water content. In other words, the soil has to be at the optimum water content for us to be able to compact it down to its maximum density. This is what this curve shows. The horizontal axis, the x-axis, is the water content increasing from almost dry to the left to saturated at the right of the axis. The vertical axis is the density of the soil that can be achieved at that water content, starting from a low density at the bottom to a high density at the top. At lower water contents, the part of the graph to the left, the aggregate is too dry and there is not enough water to lubricate the contact areas to allow the particles to slide into a denser formation when the soil is compacted. When we add more water, that is, the water content is increased, we get a higher density material. This is because there is water lubricating the contact areas, allowing the soil particles to slide into the void spaces. Even more water increases the dry density even more. However, the dry density achieved drops away as we increase the moisture content even further from the center of the graph. There is now too much water in the voids, and it is preventing the particles from coming closer together. The soil needs time to consolidate. So there is a peak in the middle where we obtain the maximum dry density, and hence the strongest aggregate layer. This water content is called the optimum water content. This is what we want the soil to be at when we compact it. When constructing a fill, we check the water content and either wet or dry the soil so that it is at or close to the optimum water content when we lay and compact it. The dry density at that point is called the maximum dry density, and this is what we expect the soil to be able to compact down to. There are charts that allow us to correlate the dry density with the bearing capacity, and this is what the designer uses when they are designing the fill to support a road.